Well, talking about shapes of molecules, VSEPR theory is a very useful and fairly easy to understand model for understanding shapes of molecules. So VSEPR is an acronym, and the E comes after the S, but it's just easier to say VSEPR. And those letters stand for valence, shell, electron, pair, repulsion. It's based on the idea that electron groups repel each other. And it's just a very simple model that helps us to predict molecular shapes. So if we look at this representation of a molecule here, here's a central atom. There's a pair of bonding electrons that are holding these two atoms together, a pair of bonding electrons holding those, and another pair of bonding electrons over here. VSEPR theory says that these pairs of electrons are repelled by each other, and that makes sense. So these are pairs of electron, but it's more important to think about electron groups. So this is an important definition of electron group. An electron group can be a lone pair, meaning it's not shared by another atom, it's just sitting on one atom. It can be a single bond, like these are. It can be a double bond that still counts as one group of electrons. It could be a triple bond, or in a free radical, it could be a single unpaired electron. Those are the groups that repel each other. And what we look at is electron groups on interior atoms. This helps us determine the geometry or shape of a molecule. So in this molecule, there is one central atom. What the electrons are doing on these terminal atoms does not affect the shape of the molecule. So preferred geometry has those electron groups separated as much as possible, and that gives you minimum energy. Any questions? Well, let's look at the 5 different shapes. The first one is called a linear geometry. Let's draw the Lewis structure for beryllium chloride. So I'm going to put beryllium in the middle and put the chlorines over here. There's going to have to be a bond in there somewhere. And then we have to think, well, how many electrons? Well, there's beryllium has 2 valence electrons, and we have 2 chlorines, and they each have 7. So that's 16. So if we start putting lone pairs around, we come up with something like this, where the chlorines have an octet, but the beryllium does not. Could this be a good Lewis structure? Yeah, because beryllium and boron often will be satisfied with less than an octet. So here it only has 4, but it often does that, so this is okay. And if we do formal charges, they're all 0, so this is good. So we look at the central atom, and we ask ourselves, how many electron groups are on the central atom? 2. There's a single bond here and a single bond there. Those are the 2 groups. The lone pairs on the chlorine don't matter. We're not going to even look at those. They can do whatever they want. They're not going to affect the shape of the molecule. So here we're looking at these 2 lone pairs. So I'm going to blow up some balloons and pause this for a minute. So when we have 2 electrons again, 2 balloons tied together, they're going to naturally separate themselves from each other. So that's what these electron groups do. They're trying to get away from each other. And this central atom is, well, one of the analogies I have for this is, so this electron group is you, and this electron group is the worst X you've ever had. Horrible, horrible person. The beryllium is the Earth. Okay? So you want to get as far away as possible from this person. You're going to the other side of the globe. You can't get any farther away on the planet. Okay? So these 2 electron groups, the farthest away they can get from each other is on opposite sides of the central atom. So here's a model of the molecule, and we see that this bond angle is 180 degrees. We call this a linear geometry because all those atoms are in a line. And this has been confirmed by experimentation. that beryllium chloride forms this linear geometry. Well, let's look at carbon dioxide. So I believe we've done the Lewis structure for carbon dioxide before. By the way, VSEPR theory requires that you look at the Lewis structure for whatever molecule you're doing. So for carbon dioxide, the carbon has 2 double bonds, one with each oxygen. So here's our Lewis structure. We look at the central atom and ask ourselves, how many electron groups? I hear 1 and 4, 2. 2 is the correct answer. This double bond is one group. And this double bond is one group. So here's our model. These 2 groups of electrons are both shared between the same 2 molecules. They can't get away from each other. They can't separate. As to why they can be so close to each other and not like explode or something, that's a different discussion. For now, just believe me. So we got this group and that group, and again, they're going to go to opposite sides of the central atom. We've got a linear geometry. Everybody okay with this? Yes?
There are 2 groups because these 2 on this side can't get away from each other, so that's 1.
Yeah, so this is one group, and this is one group. You can also go back to this definition of electron groups. So a lone pair, a single bond, a double bond, a triple bond, a single electron. Each of those counts as one group. So a group can be 6 electrons in a triple bond. It's just like one family unit, okay? Could be 2 people, could be 2 parents and 2 children, could be a dad and his mom and the 2 kids, you know, because the mom left or whatever. Different combinations, but it's called an electron group. Okay, what about 3? Let's add another balloon. So doing 3 balloons, they're going to make kind of a triangle. That's not a very good triangle, but you can try this at home. Make 3 balloons and tie them together at their necks. So the way they can get away from each other is to separate by 120 degrees. They'll make a flat structure that is triangular in shape, hence the name Trigonal planar geometry. I forgot to draw the Lewis structure for this. Let's do that real quick. So boron and fluorine. And this is another one where the octet rule is violated. Boron has an incomplete octet. Looking at this Lewis structure, we see 3 electron groups on the central atom. 3 groups separate into a trigonal planar geometry. Any questions? Formaldehyde also has 3 groups. Here's its Lewis structure. 2 single bonds and 1 double bond. So that's 3 groups, and they're going to spread apart. But this double bond to oxygen is not exactly the same as the single bonds to hydrogen. This double bond is a little more repulsive than the single bonds. And the oxygen is larger as well, and so it's going to push the hydrogens together a little bit. So their angle's 116.2, and these angles are 121.9. All the angles here add up to 360. I almost said 365, but that's days in a year. So this is also trigonal planar, but slightly different angles. Now, you do not need to memorize angles like this. But if I gave you this molecule and asked what the bond angles were, you should be able to tell me that this one, wrong pen, that this one is greater than 120 degrees, and this one is less than 120 degrees. Because the double bond is more repulsive. Okay? Any questions? 4. So here we actually have pictures of the balloons. They're even the same colors as the ones I have. So there's the two groups making a linear geometry, three groups making trigonal planar geometry. The balloons are representing electron groups. They're not representing the atoms, they're representing the electron groups. Because a lone pair is also an electron group, and there's no atom at the other end of it. When we add a fourth balloon, we no longer have a planar geometry. So adding that fourth balloon pushes the others down a little bit. If we flatten this and make it planar, then we're going to have 90-degree angles, and that's not ideal. So making it flat, the angles would be 90 degrees. It wants maximum separation. By becoming three-dimensional, we can get angles of 109.5 degrees. That's less. I'm sorry, that's greater. We want greater angles, more separation. So 109.5 is larger than 90, and so this does not happen. This is called a tetrahedral geometry. Here's a picture, a drawing of a tetrahedron. It's a three-dimensional solid, regular solid, that has four identical faces. We're familiar with cubes. Cubes have 6 faces. A tetrahedron has 4 faces. And the prefix tetra means 4. So 4 things get away from each other by making a tetrahedron. Let's look at methane. Here's the Lewis structure for methane. We look at the central atom, and there are 4 electron groups, 4 single bonds. 4 groups makes a tetrahedron. So this is a ball and stick model of the methane molecule. It's three-dimensional. It's a lot harder to draw. It's harder to draw three-dimensional things.
Isn't there like a different way to represent one of those bonds to make it right?
Yeah, there are different ways, and I'll show you that. So this is a Lewis structure. Lewis structures are flat. They have a lot of 90-degree angles. They don't represent the shape. But sometimes we don't want to have to take a picture or draw a fancy picture. Wrong pen again. And so we'll draw it like this. And your book goes over this a little later in the chapter. We'll use regular lines to indicate bonds or electron groups that are in the plane of the screen or the tablet or whatever you're looking at this on. And then we use a wedge to indicate that that one's coming out at you, and then we use a hashed wedge to indicate that this one is behind the plane. So that's the best way to draw a tetrahedron quickly. So this hydrogen, carbon, hydrogen, those are in the plane. This hydrogen's sticking out a little bit, that hydrogen's sticking back. So if I hold this, so this is one of the bonds, and this is another bond, and then this one's coming out at you, and this one's behind. They're coming apart. Any questions? So 109.5, that's your maximum separation. The Lewis structure looks flat. That's not what it's going to be. It's not stable. Just like the balloons, when I flattened them out, I made them flat like that with 90-degree angles. They weren't stable. You disturb them at all and they pop back into the tetrahedron shape. What if we have 5 electrons? 5 electron groups. So when we put 5 balloons together, the 4 have to move over a little bit to make space for this new one. So think of this as the tetrahedron. The bottom 3 had to come back up a little bit so this guy could get in at the bottom. So we've got like a trigonal planar here, and then one up and one down. So the angles here are not equal. The angles between this one and its neighbors are 90 degrees. The angles between the one at the bottom and its neighbors are 90 degrees. But these guys, these are said to be in the equatorial position. They're like around the equator of the Earth, and the axial atoms are at the north and the south pole. These are sharing 360 degrees, and so they're going to have 120-degree angles. It's the only way to maximize the separation for 5 things. So when we look at a molecule like phosphorus pentachloride and count the number of electron groups, 5 makes a bipyramidal geometry. It's 2 pyramids. So there's a triangular pyramid on the top and a triangular pyramid on the bottom. So trigonal bipyramidal. Okay, any questions? Octahedral geometry. So the 6 balloons representing the 6 electron groups.
So now they're all 90s.
They're all 90s now. All of the angles are 90 degrees. So sulfur hexafluoride has 6 single bonds, 6 electron groups. 6 things get away from each other by making a shape like this. So this is an octahedron. It's like 2 pyramids, 2 square pyramids stuck together. So this top is a square pyramid and the bottom is a square pyramid. The last one, the trigonal bipyramid, was 2 triangular pyramids. This is 2 square pyramids, but it's called an octahedron. Okay? Here we have all the electron groups having the same separation. Question?
So then the 2 fluorides on the top, on the sides, are drawn with that little going towards the back, and then the 2 next.
Yeah, so this one's going back, and you can, they indicate this because the stick here, we can see where it enters the ball. On the forward-facing balls, where it joins the ball is hidden. And this one is behind, and this one is in front.
I mean, on the Lewis structure, when you...
The Lewis structure is just, this is this flat. Now, if you want to draw this, then you would have the sulfur in the middle, and a fluorine up, and a fluorine down, and a fluorine sticking out in the front, and a fluorine sticking out in the back, 2 in the back and 2 in the front.
Okay, yeah, that's right.
Once you get the image of the balloons in your head and get that shape in your mind, then when you look at one of these representations, you can understand it. Otherwise, something like this looks like some scribbly stuff, right? It's a representation of something. Yes?
I don't understand how it would be 90 degree all around, because the balloon back looks like it's on top and on the bottom, and it kind of stick out, so I feel like it's...
Well, the angle from this to this would be 180, but from this one to that one is 90, and from this one to that one is 90. And between any 2 adjacent fluorines, the angle will be 90 degrees.
So that's like a dice. That's 6.
Well, yes and no.
1, 2.
It's not like like dice because the sides are triangles. And a die has 6 square sides. And these are triangular.
About 7 electrons
We're not going to do 7.
that exist.
Not sure. Not sure. In theory, sure, but I don't know. Let's determine the molecular geometry of carbon tetrachloride. So the first thing you have to do is draw the correct Lewis structure. So we'll put carbon in the middle, and chlorine on each side, and chlorine above and chlorine below, just kind of spreading them around. And then we have to identify how many valence electrons are there. Well, the carbon has 4. There are 4 chlorines. They each have 7. So we have 28 plus 4. We have 32 electrons. So we already have 2, 4, 6, 8 for the bonds. And now we start putting lone pairs. 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. We don't need any multiple bonds. If you check the formal charges, they're all going to be 0, and everybody is fulfilling the octet, so it's all happy and good. That's step 1. Then we look at this and we ask ourselves, how many electron groups are around the carbon? 4. How do 4 things get away from each other? Tetrahedral. So this molecular shape is tetrahedral. Any questions?